All right, we are going to wrap up chapter 14 today, and we are going to look at section 8, which is acidic and basic properties of salts. So we're going to do a couple of things in this section. The first is we're going to look at classifying a salt, and then after that, we're going to look at how to find the pH of our salt. So let's simply start by just defining a salt as kind of a review of what we should know. Okay, so in chemistry, we know that a salt, or the term salt, refers to any ionic compound. Okay. We should know that a salt will dissociate completely in water. And the new part we're going to learn today is that the ions produced from a salt can behave as an acid or a base. All right, so let's talk about categorizing salts. And we're going to break this down into some steps. So the step number 1 is we want to write a dissociation equation. And the benefit of this is that we'll be able to see what the cation and the anions are. All right, then step number 2, we are going to cross out pH spectators. pH spectators. All right, so we're going to make ourselves a little chart of pH spectators. All right, so we're going to talk about what pH spectators are if they're a cation. Now, in order to be a pH spectator that's a cation, you have to be a cation from a strong base. And the reason why they're spectators is that they have no affinity for hydrogen ions. So in other words, they don't have any attraction for hydrogen ions. Okay. And they also don't have the ability to produce hydrogen ions. So that OH bond is strong. Okay. And since it doesn't attract hydrogen ions, it doesn't produce hydrogen ions, it has no effect on pH. All right, so we should easily be able to generate a list because we know that the metals that make a strong base all come from group 1. So that would be lithium, sodium, potassium, and rubidium. And the metals from group 2, which would be magnesium, calcium, strontium, and barium. Now, we can also have pH spectators that are anions. And these would be anions that come from a strong acid. And they have no affinity for protons. In other words, they have no affinity for hydrogen ions. Okay. And if they don't have any affinity for hydrogen ions, then they have no effect on pH. All right, so you have to know your strong acid list. So HCl, so that means the anion would be the chloride ion. HBr, so the bromide ion. HI, so the iodide ion. HNO3, so the nitrate ion. HClO4, so ClO4. H2SO4, so the SO4 negative 2 ion. Okay, so you're just going to need to memorize your, again, if you know your list of strong acids and you know what makes a strong base, then you easily know your pH spectators. Okay, so now let's be specific about classifying. So that's the step number 3 part. And then we're going to look at some examples. Okay, so here's the first example we're going to look at. So my salt is CH3NH3Cl, and I'm going to follow the steps. So we are going to write its dissociation equation. Okay, it looks like at the top I have the wrong salt listed, but I want to use the salt that's in my picture. So it's CH3, CH2, NH3, Cl. And so we're going to write its dissociation equation. So my anion is this chloride ion. And we're left with CH3, CH2, NH3. And that's going to have a +1 charge. All right, step number 2. We're going to cross out the spectator. So the spectator here is the anion. And so that means the player for pH is the cation that I have. Right? So this cation is going to react with water. And this cation has a +1, which means it has a hydrogen ion to give away. So we form the hydronium ion. And you're left with CH3, CH2, NH2. And so because we make this hydronium ion, this would be an acidic salt. Okay. So this cation is a conjugate acid of a base. And the cation has a proton to donate. Okay, let's look at my next example. So we have a salt. We're going to write its dissociation equation. Okay, so this sodium breaks off. And we're left with CH3COO negative. And the sodium is from a strong base, so it crosses out. And the CH3CO, we should recognize this as the acetate ion. So this is actually a conjugate base of a weak acid. So it's going to behave as a base. Okay, so in other words, in this case, when it reacts with water, it's going to be the proton acceptor. So we form CH3COOH. And when water gives up a hydrogen, you're left with hydroxide. So the fact that we produce hydroxide makes this a basic salt. Okay, let's look at a couple of other scenarios that we could have. So we could also have this scenario where I have NaCl. In water, it's going to dissociate to give you a sodium ion, and it's going to give you a chloride ion. Sodium comes from a strong base, so it crosses out. The chloride comes from a strong acid, it crosses out, so this would be a neutral salt. And so for neutral salts, there's no pH calculations because we should know that the pH of a neutral substance is 7. All right, now we can have both ions that are spectators. And we can have it where both ions affect pH. Okay. Now, to figure out, and we're just categorizing. So we need to just be able to identify if it's an acidic, basic, or neutral salt. So for here, we're going to compare the Ka value and the Kb value. And so here are our scenarios. We can have a scenario where Ka would be larger than Kb. And in that case, our salt would be acidic. You can have it where Ka is equal to Kb, and in that case, it would be neutral. And again, the pH here, there would be no calculation. You would just tell me it's equal to 7. And you can have a Ka that's smaller than Kb, and in this case, you're going to have a basic salt. Okay, so let's look at some scenarios so we can determine. So let's look at this. My salt here is ammonium acetate. So my salt breaks apart into the ammonium ion and the acetate ion. And neither of these come from a strong acid or strong base. Ammonium is the conjugate acid of ammonia. And the acetate ion is the conjugate base of acetic acid. Now, In the case of ammonium, it actually has a Ka value that you can look up on the chart. It would be equal to 5.6 times 10 to the negative 10th. But for the acetate ion, there is no Kb value. So we have to actually calculate Kb. So here's probably the new part we're going to learn in this section. If I take the Ka and multiply it by Kb, it should be equal to our ionization constant for water. So if this is a conjugate base, we need a Kb value. So we have 1 times 10 to the negative 14th. And we're going to divide it by the Ka. And you're going to have a Ka value for this acid. You can look it up in your table. It is 1.8 times 10 to the negative 5th. So when I solve, I get 5.6 times 10 to the negative 10th. And so in this case, Ka is equal to Kb, so this salt would be neutral. Okay, so that's scenario 1. Let's look at scenario number 2. So in scenario number 2, my salt is ammonium cyanide. And so again, we dissociate and we get the ammonium ion and we get the cyanide ion. And so we, again, want to reiterate that ammonium is the conjugate base of the weak acid ammonia. And it actually has a Ka value of 5.6 times 10 to the negative 10th. And cyanide is going to be the conjugate base of HCN. And so HCN is going to have a Ka that's equal to 6.2 times 10 to the negative 10th. Now, if this is a conjugate base, we're going to need a Kb value. So we're going to take Kw and divide it by Ka. And we're going to get 1.6 times 10 to the negative 5. So in this case, my Kb value is bigger than my Ka value. So this means my salt is basic. Okay, and then I have one other scenario that we want to look at. So in this case, my salt is aluminum sulfate. And we recognize this SO4. It is the anion of a strong acid. And so that means it's a spectator, so we can cross this out. And this aluminum ion is considered to be a highly charged metal. And so highly charged metals would be anything that has a charge of +3 or greater. And we'll look at the equation for this when we're looking at our practice problems. But highly charged metals have the ability to create hydrogen ions in solution. So that makes this acidic. Okay, so we've kind of talked about all the key components that we're looking for in order to classify our salt as acidic, basic, or neutral. So now we're ready to look at some problems. Okay. So the first problem is, now I'm not in the problem going to tell you it's acidic or basic. You're going to have to figure that out on your own. So we'll have that discussion first, but this is where we're going to calculate the pH of a basic salt. So I tell you the salt is Kf. So again, it's just like classifying. You want to write your dissociation equation. And we should recognize that this potassium ion comes from a strong base, so we're going to cross it out. But this fluoride is a conjugate base of a weak acid. And we should recognize that the weak acid is HF. Okay. So this fluoride ion is going to react with water. And the fluoride ion is going to be your base. So it's going to be the proton acceptor. We're going to make HF. And when water donates a hydrogen, you're going to have the hydroxide ion left over. Okay. Now, because this makes hydroxide, you're going to need a Kb value. So Kb, we can find that by taking Kw and dividing by Ka. So Kw is 1 times 10 to the negative 14th. And I gave you the Ka in the question. I tell you it's 7.2 times 10 to the negative 4th. And so Kb is going to be 1.4 times 10 to the negative 11th. Okay, now for this, we're going to need to make an ice table. And so the concentration of my salt was 0.3 molar. And if I look, everything in this equation is in a 1-to-1 ratio. So that means the concentration of fluoride is also going to be 0.3 molar. Okay. Now, we don't have to worry about water. It's a pure liquid. We have no HF or hydroxide in the beginning. The fluoride ion is going to react with water, so it's going to decrease. And we're going to produce HF and produce OH. And again, the coefficients in front of my x's are going to be 1s because the coefficient in my equation is a 1. So I get 0.3 minus x, and then x, and x. All right. So my Kb expression would be HF times OH over the concentration of the fluoride ion. And Kb is small enough where we can use approximation. So we're going to have x squared on the top and then 0.30 molar on the bottom. So you're going to need to solve for x. So you can pause your video here while you plug and chug out an answer. And you should get that x, which would be equal to the hydroxide ion concentration, is 2 times 10 to the negative 6 molar. And you're actually going to need to find pH. So we're going to use the steps that we've used earlier in the chapter. So I'm going to choose to do this. I'm going to find the pOH first. So I'm going to take the negative log of 2 times 10 to the negative 6. And the concentration has 2 sig figs. So your answer should have 2 decimal places. So again, you can pause your video to make sure you get an answer of 5.69. And then if I subtract that from 14, this is going to give me my pH of 8.31.